Okay, so we move on to the next part of the chapter, that is in the radioactive part. The next part was nuclear fission and fusion. We can consider it as a completely different chapter as such because it has no connection with the previous part except for the fact it is connected to the nuclear activity. And it is a part of the modern physics. So yeah, this was the B part of the modern physics chapter, that is nuclear fission and fusion. So nuclear energy, first of all let's understand what is nuclear energy and then we'll talk about fission and fusion. Fission is basically splitting, fusion is fusing, that is combining. So that's the nuclear energy what we are going to get when we are splitting the atoms or when we are connecting the atoms is nothing but the nuclear energy. So we are getting energy, we generate energy, we are able to generate energy when you are going to split the atom, at the same time when you are going to combine the atom. So when you are going to split the atom, it is nuclear fission energy, and when you are going to combine the atom, it is nuclear fusion energy. So nuclear fission and fusion, nuclear energy. In the nuclear change, due to a radioactive phenomena such as decay, fission or fusion, the total sum of masses of product nuclei is always less than the total mass of the masses of the reactant nuclei. Thus, there is a loss in mass. Yes, this is it. Up till earlier time, we were just saying that mass can neither be created nor be destroyed. Then we said energy can neither be created nor be destroyed. But now we are saying that mass and energy, some can neither be created nor be destroyed, but they can be interchanged between each other. That means mass can get converted into energy and energy can get converted into mass. That is the basic principle what we are using in nuclear energy. Okay, and it is mainly going to be given out by the formula E is equals to mc square. Okay, the main important formula, which is going to be Einstein's formula, that is E energy is equals to mass into speed of the light, c is speed of light square. So thus there is a loss in mass. In 1905, on the basis of the theory of relativity, Einstein suggested that mass and energy are interchangeable. Due to loss in mass, delta m, the energy released is E, where E is equals to delta mc square, where delta m is the loss in mass in kg, c is the speed of light 3 into 10 to 8 meter per second, and E is the energy in joule. The energy so obtained is called as the nuclear energy. So let's see that what is the energy given out by a body when there is a loss of mass by 1 kg. So if we talk about that thing, it's very simple. So we know that here I'm going to say delta over here because this is the change in mass. So when we take this particular thing, we know that E is equals to delta mc square. So if this delta m is 1 and c is 3 into 10 raised to 8, 3 into 10 raised to 8 meter per second, the whole square. So it will be 3 के बदले हो जाएगा 9 into 10 raised to 16 joule. So that will be the thing, that 9 into 10 raised to 16 joule, and we know that 1 kilowatt hour is equals to 3.6 into 10 raised to 6 joule. So accordingly, we can see that on calculating we find that the energy given out by 1 kg will be equal to 2.5 into 10 raised to 10 kWh. So that's a huge amount of energy. You can imagine now that if 1 kg of the nuclear material can give you such a huge amount of energy, so that's why we ought to have nuclear power plants. But of course, due to the problems with the nuclear waste and all, we are restricting on that. So energy equivalent mass of 1 kg when 1 kg of mass is lost, the amount of energy released is equals to delta mc square is 1 into 3 into 10 raised to 8 meter per 8 into 2 raised to 2 is equals to 9 into 10 raised to 16 joule. Since 1 kilowatt hour is 3.6 into 10 raised to 6 joule, therefore the energy is equals to 9.6 9 into 10 raised to 16 upon 3.6 into 10 raised to 6 kWh is 2.5 into 10 raised to 10 kWh. Thus, 1 kg mass is equivalent to 9 into 10 raised to 16 joule or 2.5 into 10 raised to 10 kilowatt hour of energy. Energy equivalent to 1 mass of AMU. So that instead of 1 kg, if we just say 1 AMU, that is 1 atomic mass unit. So 1 AMU is 1/12 of the mass of a carbon atom. So it is 1/12 of 12 into 10 raised to minus 3 kg upon 6.02 into 10 raised to 26 per kg mole. So that is 1.6 into 10 raised to minus 7 kg, 27 kg. We have already seen that mass of one proton, 1.6 into 10 raised to minus 27 kg. Due to the loss of mass of delta 1, so it will be 1.6 into 10 raised to minus 27 into 3 into 10 raised to 8 the whole square. So that comes out to be 1.4 into 10 raised to minus 10 joule. So that will be 1 mega electron volt is 1.6 into minus 13. So that's why we have this thing as energy is 1.49 into 10 raised to minus 10 upon 1.6 into 10 raised to minus 13 mega electron volt. That is 1 AMU, 1 atomic mass unit gives out 931 mega electron volt. Okay, this is the amount of energy which is going to be released by one atom. Okay, we are talking about just one atom. Okay, one atomic mass unit. One atom means not even one actually particle, one proton jitna one. Okay, that is one hydrogen atom. We can just say one hydrogen atom. Thus, 1 AMU of mass is equivalent to 931 mega electron volt of energy. The mass of an electron, proton and neutron in terms of kg, AMU and megavolts are as follows. So, electron will be 0.511 mega electron volt. Mass of proton will be 938.3 mega electron volt. Mass of neutron will be 933 mega electron volt. To summarize, we get electrons is in kg 9.1 to 10 raised to minus 31. AMU is 0.00055. Mega electron 0.511. You don't need to learn this thing, not a problem. Protons 1.6725 into 10 raised to minus 27 kg. 1.00727 AMU 938.3. Neutron 1.6748 into 10 raised to minus 27. 1.00865. 939 is the total. So that is about the masses of the particles of the atom. Now let's start with the next part, that is the nuclear fission. Okay, now we talk about nuclear fission. Nuclear fission is a process in which a heavy nucleus is splitted into two light nuclei the nearly same size, but by bombarding it with a slow neutron. In each fission reaction, a tremendous amount of energy, that is 190 mega electron volt, is released. So in a nuclear fission, you are having one particular atom which is bombarded, and then bombarded is by a slow moving neutron. A slow neutron is bombarded on it, so that breaks this into two almost equal parts, and on breaking down there will be an amount of energy which will be released. That energy which will be released will be quite high, that will be around 190 mega electron volts. The reason for the release of energy is that the mass of the sum of the masses of the product nuclei is less than the sum of the masses of the parent nucleus and mass of neutron. That is a loss of mass in the reaction. This loss in mass is converted into energy by the Einstein's mass energy relationship, E is equals to delta mc square. In 1939, Strassman and Hotham found that when a slow neutron strikes the uranium-235 nucleus, it gets absorbed in it, and a most unstable isotope 236 uranium-92 is formed, which splits into two nuclei, barium-14456 and krypton-8936. With the release of three neutrons, and a tremendous amount of energy as shown in the figure. The fission reaction is expressed as follows. So that is what they are given you. So let's see that. So they say that if the uranium atom, so they have got a uranium atom that is 2. The uranium atom 235U92 is bombarded by a neutron. So when it is bombarded by a neutron over here, it is going to split up, and on reacting it is going to give me two things. One will be 144 barium 56, and it is going to give me plus krypton. So krypton will be A1 8936. Okay, and with this there will be 3 other neutrons which will be given to me. So there will be other 3 neutrons plus energy. Okay, now add it up. 235 plus 1, 236, and over here is going to be like this: 3 plus 89 to 92 plus 2 plus 4 is 96. Yeah, 236, right? And this 2 also becomes 92. So you can see that after production of this and this, there was 3 atomic mass unit lost. There was a loss of mass by 3 atomic mass unit, that is nothing but 3 neutrons. 3 neutrons are going to be released when this particular uranium splits into this 2. And that 3 which is given out, it gives out a huge amount of energy as against its mass. So the mass K against जो change आएगा, that will be equal to, in the form of E is equals to delta mc square. Later on, it was found that uranium-236-92 isotope decays not only into barium-144-56 and krypton-89-36 fragments, but it can decay in different pairs of nuclei such as barium-141-56 and krypton-92-36, lanthanum-148-57 and barium-85-35, for which nuclear reactions are given below. So you need not, you can just learn this thing as such, but up till now the number of times the board exams have come for this one is only 3. So, and in this one they have got only once it was asked, this one of the reaction that this one was asked, but otherwise they are not asking you. So you may skip the later part, the 2 parts, that is uranium-35 वाला चेंज होके बेरियम और क्रिप्टन बनता है और lanthanum and bromine बनता है, that you can skip, that you can always avoid. But the first one, yeah, you can learn this part. So uranium-235-92 and 1 neutron will give you uranium-236-92 to give you 141-56 barium and krypton-92-36, and the next plus energy, and the other one could be uranium giving you lanthanum 148-57 and bromine 85-35 plus energy. In each fission reaction, the atomic number Z and mass number A remains conserved. Yes, you can see this. In this whole reaction, the complete thing, the total of this is equal to the total of this. There is no loss as such. Okay, the reaction, the mass number is the 2 fragments obtained on fission of 1 uranium-235 are unstable and they emit beta particles and gamma to become stable. So this is not the end of it. They keep on, these also keep on giving out beta radiations and gamma radiations on further because they are still unstable. And you can know that thing because this is the difference between the, you can see 144 minus 56 is something like 90 or 88. So utna jada difference between the 56 protons and 88 neutrons. So difference is very high. Here also the difference is very high because the double of 36 is only 72, is 89. So automatically when there is a difference, huge difference between the protons and neutrons, definitely it is going to give rise to a reaction which will have more amount of radioactive material. So the radioactivity will keep on continuing. The next is nuclear energy obtained in one. So we see the nuclear energy obtained in one fission reaction of uranium-35. So let us understand or let us calculate the amount of energy which is going to be given out by 1 nuclear reaction of uranium. Due to fission of one uranium nucleus, nearly 190 mega electron volt energy is released. The cause of emission of this energy is the loss of mass, that is, the sum of masses of product nuclei is less than the sum of masses of the parent nuclei and the mass of the neutron. Consider the fusion reaction 235 uranium 295 nucleus as 235 plus 1 neutron, so this particular equation. If we take the mass of neutron 1.01 AMU, mass of uranium 235 is 234.99, barium is 144 is 143.87 AMU, mass of krypton 89 is 88.90 AMU. Then the loss of mass in fission reaction of one nucleus is equals to mass of uranium today plus mass of one neutron minus mass of barium plus mass of krypton plus 3 neutrons. So accordingly, if you add it up, you get that the difference is 0.2 AMU. Okay, the total mass difference is 0.2 AMU. But from the mass energy equivalence, we know that 1 AMU is 931 mega electron volt. So if 1 AMU is 931, so 0.2 will be how much? That will be 190 mega electron volt. So this is how we are going to get that difference, or we are going to get the energy which is going to be released by one such nuclear reaction. In the fission of one 235 uranium nucleus, nearly 190 mega electron energy is released. The major part of this energy is obtained in the form of kinetic energy of the fragments obtained from the fission, and the remaining part is obtained in the form of kinetic energy of the neutrons emitted, that is gamma rays, heat and light. Okay, so this is about the how the heat, or you can say the energy is going to be released by the nuclear reaction. Okay, one sec. So we move on to the notes now. 1. Due to fission of 1 gram of uranium 235 92 is equals to 2.56 into 10 raised to 21 nucleus, nearly 4.8 into 10 raised to 23 mega electron volt energy is released, from which 2.1 into 10 raised to 4 kWh, it's 21,000 kilo elect volt, that is 21 megawatt ampere megawatt hour electric energy can be obtained. Actually, this much energy is generated due to the explosion of nearly 20 tons of TNT, that is trinitrotoluene. So you can imagine that how much amount of energy can be produced. It is equivalent to 20 tons. This is just 1 gram of uranium. 1 gram of uranium can give you a amount of explosion which can be done by 20 tons of trinitrotoluene. So that's a huge amount of energy which is generated, and that's the reason why the nuclear bombs are so dangerous. A use of nuclear bombs will be just devastating because of this particular reason. The ore of uranium found in nature contains two isotopes, 99.3% 238 uranium 92 and 0.7% 235 uranium 92. Although both the isotopes are fissionable, but experimentally it is found that the isotope 235 92 is more easily fissionable than uranium 238 92. The reason is that the fission of 238 92 nucleus is possible only by fast neutrons, while the fission of 235 uranium nucleus can be even by a slow neutron. So yes, we have got maximum amount of 235 in the mines of uranium, so that is 99.3% is 238. Yeah, 238 is maximum is 238, 99%, but the 0.8% जो है, 0.7% जो है, they are much more used for fissionable because they can even be bombarded by a slow moving neutrons rather than a fast moving neutron. The 238 requires a fast moving neutron, whereas this requires a slow moving neutron. Now we can see over here that this process is going to be a chain reaction. Why it's a chain reaction is because It is that one uranium atom is going to split into two parts and become barium and krypton. And it is going to give rise to three neutrons. Now here what happened, we had made one neutron to bombard over here to uranium to give you this. So these neutrons which are going to be given out, they are going to hit the uranium which is there. So there is no only one atom of uranium. We have got multiple, there's a uranium rod altogether. So this neutron is going to hit another uranium and give you further 3 neutrons. This is going to use another neutron and further 3 neutrons. Again here also. Similarly, this will again hit another. So that's why one neutron over here is going to give rise to 3, 3 giving rise to 9, 9 giving rise to 27, and hence the reaction what is going to take place, the fission reaction which is going to take place is a chain reaction, and that chain reaction is tremendous that it will just be a huge explosion. And if such a thing is there, then it is not possible for you to extract the energy so fast. And that's the reason we have developed the method by which you can control this particular reaction. So what they do in the controlling is that they are going to absorb 2 of the neutrons which are going to be given out in this reaction. Control it. So it only hits 1. Again, 2 are controlled. So again it hit 1. So it is just hitting 1, then 1, then 1 and 1. That is called as a controlled reaction. So that's why the nuclear fission can be of 2 kinds. One is a uncontrolled nuclear reaction, another is a controlled nuclear reaction. So controlled and uncontrolled chain reactions. We have read that when slow neutrons are bombarded on uranium-235, each uranium nucleus splits into 2 nearly equal fragments of barium-144 and krypton-89, with a release of 3 new neutrons and tremendous amount of energy, nearly 190 mega electron volt. These new neutrons can cause fission in other uranium nuclei under the suitable conditions. Thus, a chain of fission of nuclei is formed, which once started continues till the entire uranium is consumed. Hence, the energy obtained from the nuclear fission continuously increases. Due to such a chain reaction, a strong explosion of entire uranium occurs in a very short interval of time, and tremendous heat, high energy is released, which can be very harmful. This is uncontrolled chain reaction a nuclear bomb is based on. So nuclear bomb is based on this reaction, where it is a chain reaction which is uncontrolled and everything just explodes in a very fragment of a short duration of time. And that's why the huge energy which is generated over there can be devastating. If the chain reaction is controlled by absorbing some of the neutrons emitted in the fission process by means of cadmium rod, and then making them slow by the moderators such as graphite, heavy water, etc., the energy obtained in fission can be utilized for the constructive purpose. This is a principle of nuclear reactors. So the nuclear reactor which are there in the power plants, they work on the principle of controlling the nuclear reaction by absorbing the neutrons which are emitted by the reaction. So out of the 3, 2 of them are going controlled by use of cadmium rods or heavy water, cadmium rods, and they are going to be slowed down. They are not fast moving. They are fast moving, so they are slowed down. They are moderated, and that moderation is done by the use of graphite or heavy water. And accordingly, they are using this energy for constructive purpose, which is a nuclear reactor. So the use of the fission. The tremendous amount of heat energy released in the process of fission can be used in 2 ways: the destructive use and the constructive use. For destructive use, the fission process is used in a nuclear bomb, sometimes also called as the atom bomb, but the word atom bomb is a misnomer where the energy release is fast and uncontrolled. So normally you told it as actually it's a nuclear bomb, but yeah, atom bomb is just a Miswell, because it is not the atom which is going to split, it is the nucleus which is going to split and give you the energy. For the constructive use, the fission process is used in the nuclear reactor, where the rate of release of energy is slow and controlled. This energy is used for generating the electric power. So this is how the constructive use of the nuclear fission is taking place. Now let's understand what is the difference between the nuclear fission and the radioactive. See, here we saw that okay, the uranium, the atom got split into two. There was a nuclear reaction also taking place. It was the nucleus which got split. But here there is no alpha, beta and gamma radiations. Okay, they are not the same. So that's why nuclear reaction, that is of nuclear fission or fusion, is different from the radioactive thing. So let's see what is the difference between them. Although both the radioactive decay and nuclear fission are the nuclear phenomena, but they differ as follows. Radioactive decay, it is a spontaneous process. Suddenly it just takes place and then it starts radiating out. Whereas nuclear fission, it does not occur by itself. It is initiated when neutrons are bombarded on the heavy nucleus. It requires the neutron to be bombarded on this heavy nucleus so that it splits into two. So it is not something which is going to be spontaneous. It is not going to be something which is going to be naturally occurring. It is just man-made. You know, we are doing that thing. We are purposely doing that thing. Radiative decay, the nucleus emits either the alpha or beta particles with the emission of energy in the form of gamma rays, which is not very large. So yeah, the energy which is given out by the alpha, beta and gamma, they are not very large. They don't give you a large amount of energy. Okay, they are high amount of penetrating power and all. They can damage things, but they don't have the high amount of energy given out by that thing. Whereas on bombardment of heavy nucleus with the neutron, a tremendous amount of energy is released, and the nucleus splits into two nearly equal fragments. Third one is the rate of radioactive cannot be controlled, whereas the rate of nuclear fission can be controlled. So this is about the differentiation between radioactivity and nuclear fission. Okay, so that was about the first part of the chapter. Now we see to the next part of the chapter, that is the nuclear fusion. I'll just check the timings if I can continue this or the next video. Yeah, I'll stop over here. We continue in the next video.